Welcome back to my kitchen. So, have you ever noticed how in a faucet, very close to the tip of the faucet, the fluid is pretty wide, but then as the stream of water gets down, that fluid gets narrower, the stream gets narrower and narrower and narrower, and then it gets turbulent and breaks up into droplets later on. But have you ever wondered, is there some mathematical function that describes the thickness of the curve, the thickness of the fluid stream as it goes down, and perhaps also the velocity of the fluid stream? So, let's actually go ahead and solve that today. So, let's figure out, hey, what is the thickness, what is the diameter of the stream, and what's the velocity of the fluid as it falls? So how do we go about figuring out the diameter and velocity of the stream of fluid exiting downward from a faucet? Well, we need to take a quick detour first to talk about a new concept that's in fluid mechanics, and this concept is that of conservation of energy. So you've all taken mechanics courses before. You know that in mechanics, if we do some work on a system, the work that we do on a system results in some change in energy of the system. Right? And work, if we remember, work is basically equal to like a force dot distance, if those are constants, or an integrated force over a distance if it's some variable. And the energy of a system comes in different flavors, right? So work is basically related to force and distance that force is applied over. And the energy of a system comes in many flavors, and in particular it comes in terms of potential energy and kinetic energy. So, in mechanics, we often talked about like particles and like particles on springs and going up and down hills and rolling and things like that. In fluid mechanics, there's an analogous thing for conservation of energy, but rather than sort of framing it in terms of work and a change in energy of potential and kinetic energy, we oftentimes in fluid mechanics frame it in a way that we did before. Rather than in terms of work and energy, we frame in terms of rates. So we oftentimes frame this in terms of rates in fluid mechanics, and it would be basically rates for a control volume. And we'll talk about a very detailed version of this in a future lecture, but you can basically say, hey, there's a rate of accumulation, a rate of energy accumulation, and that's going to be equal to the rate of energy in minus the rate of energy out plus the rate of energy generated within our control volume. So we can frame energy in the same way that we framed, at least qualitatively, we could frame it in terms of all our other ones. And again, in a future lecture, we're going to do a very detailed analysis. But let's look at sort of a special case today. So we'll do the full version in the future, but today we'll look at a special case of conservation of energy for fluids. And the criteria for this special case are pretty restrictive. We're going to have an incompressible homogeneous fluid, which is basically saying that density is equal to a constant. All right, this assumption basically comes around all the time, so not particularly restrictive here, but we're also going to consider only steady systems today, so none of this, there's not going to be any accumulation if we're in some kind of steady state. We're also going to consider only cases where we have where we're doing no where we have no sort of friction, viscous dissipation, or turbulence. And this is actually a very restrictive, right? You know, how often in real life do you come across fluids where there's precisely no friction, you know, essentially no viscosity or viscous effects in the fluid? Almost never. But under some circumstances, it's not that there's no friction, it's just that the friction is negligible enough for this assumption to basically work. So, and then the final thing is we're going to analyze fluid, we're going to analyze points that belong to a single streamline. And by streamline, I mean this is essentially like a path that a fluid particle takes. I guess not strictly speaking, there's a slight difference here, but in steady state, you can consider this like a path of particles. In a steady flow. So if you apply the idea of conservation of energy to an incompressible homogeneous fluid in steady state, where you're neglecting any sort of friction dissipation and you have no turbulence or minimal turbulence in your flow, and you're analyzing points that belong to a streamline of particles, conservation of energy becomes a very an equation that you might have heard before, the Bernoulli equation. So if you can make this set of assumptions, then you can use the Bernoulli equation to relate energy, work, etc. on a flow. So let's plop down the Bernoulli equation and explain what some of the terms mean. So here's the Bernoulli equation. The Bernoulli equation analyzes points that belong to a streamline. So let's just imagine we had some flow. Let's just imagine that we had some flow with a couple of streamlines, right? And you know, fluid kind of moving along this flow. The Bernoulli equation would relate 2 points on the flow. So, you know, let's say, or 2 points in the flow and 2 points that belong to some particular streamline. And when we're identifying these points and using the Bernoulli equation in fluid mechanics, it's oftentimes very useful to number the points. So, you know, point 1, point 2. So in the same way that you define faces when you're doing control volume problems, it's oftentimes useful to very explicitly define the points when you're using the Bernoulli equation. And the Bernoulli equation is as follows. It's the pressure at point 1 plus 1/2 rho times the magnitude of whatever velocity we have at point 1 squared, velocity squared, plus rho g h1, and this is equal to pressure at point 2 plus 1/2 rho times whatever velocity we have at point 2, that squared, plus rho g h2. So this is the Bernoulli equation right here. And so what are some various points here, or some various quantities here? These are the pressures, the pressure at points 1 and point 2. These right here are the fluid velocities. So, you know, at point 1, the fluid has some particular velocity, v1, and at point 2, the fluid has some particular velocity, v2. If I essentially take their magnitudes and square them, that's what these two terms are in here. And of course, these are, this is the fluid density.
And then if I say, hey, this flow, let's sort of say this flow exists in a gravitational field, right? We're on Earth. Gravity, let's say, is pointing down, something like that. And I might consider the z positions of fluids, right? So let's say above some base level, h1 is the height of the fluid here, and h2 is the height of some point in this flow here. Those are the heights that I'm talking about here. And g is gravitational acceleration, that 9.81 meters per second squared that we've seen all along. So h's are essentially heights in a direction that is sort of against the direction of g. So that's what these terms mean. So basically, if we have these flows, we can relate pressures at different points in the flow, velocities at different points in the flow, and height levels at different points in the flow. So take a moment now, pause and ponder. What are the units of terms in Bernoulli? What are the units of each of the terms in this equation here? Well, if we work it out, the pressure terms, of course, have units of pascals or newtons per meter squared. If I think about rho times the magnitude of some velocity squared, that's going to be kilograms per meter cubed times meters squared per second squared. And if you cancel, if you sort of cancel everything out, or do all the same stuff, it ends up being equal to a newton per meter squared. And then if you do rho gh, then you end up with kilograms per meter cubed, meter per second squared, and meters, which also have newton per square meter. And, newtons per square meter, like we can interpret this as a pressure in some way, right? So in a sense, there's, the kinetic energy of fluid, can sort of go back and forth between pressure and potential energy. But interpreting Bernoulli as newton per meter squared, I find actually somewhat unsatisfying. So let's take a closer look at this term. If you dust off your notes from mechanics, biomechanics, whatever, what does this term start to look a little bit like? Especially if, hint, if we're thinking about energy. What does this term look like? So pause and ponder if you care. Well, if we think about this term, if you think about kinetic energy of a particle, that was 1/2 mv squared. And here we have these 1/2 rho v squared terms. So in a sense, this 1/2 rho v squared term, I like to think of this as the kinetic energy of fluid per unit volume, right? So this is essentially like a kinetic energy per unit volume, right? If density is mass per unit volume and kinetic energy is 1/2 mass velocity squared, this 1/2 rho v squared is essentially the kinetic energy of the fluid per unit volume. So rather than interpret things in terms of newtons per meter squared, I could interpret it as newton meters per meter cubed, or equivalently joules per meter cubed. And this is really the interpretation that I like for Bernoulli equation. So take a moment now and pause and ponder, what does this term look an awful lot like? Perhaps you could dust off your mechanics notes. Well, if you look at this term, if we talked about the potential energy, the gravitational potential energy of a particle, then the gravitational potential energy of a particle was mgh. Well, if we look at potential energy per unit volume, mass per unit volume is just density, so I like to interpret this as the potential energy, the gravitational potential energy per unit volume of fluid. So in the same way that particles can have potential energy, chunks of fluid can have potential energy. And in the same way that particles can have kinetic energy, chunks of fluid can have kinetic energy. And we can have exchanges. If I have some flow here and it transitions to a different part of the flow, I can have exchanges between potential energy and kinetic energy. And what might actuate changes in fluid? Well, if we talk about conservation of energy, the changes of energy of the system, those can be potential or kinetic. What accomplishes or what enacts those changes of energy? Work. And it's basically pressure, this force per area, that does the work. So it's pressure that does the work, the work to change energy. So in a sense, Bernoulli equation is basically saying, hey, if I did some work, some net work on this chunk of fluid to bring it from here to here, how would its kinetic energy change and how would its potential energy change? So basically how much work, i.e. how much pressure, it's kind of like a work-like term in fluids, how much work is needed to change the kinetic and potential energy of this fluid. So that's the essence of the Bernoulli equation. And of course, this is an energy conservation equation because it's basically saying, hey, all the energy and the work done is conserved. If we had any friction effects or viscous dissipation or turbulence that was dissipating that energy, then we would need to include some kind of correction term in this equation to account for fluid friction losses. And for now, we're not going to include those. We're going to sort of use this only under a very restricted set of circumstances. But when we go through the full conservation of energy, the more detailed derivation that we're going to do in a future lecture, will account for friction, viscous dissipation, turbulence, all of that stuff. So, Bernoulli equation. Let's use it. So here's conservation of energy, and with a very restrictive set of assumptions, we get a Bernoulli equation. And spoiler alert, the Bernoulli equation is going to be useful for the Faucet problem that we were trying to solve earlier. So let's talk about this Faucet problem. So imagine I have this faucet right here, and I know that as water drips out of this faucet, the jet sort of starts off with the diameter of the faucet here, but you saw that it kind of narrowed down as the fluid kind of went farther, got farther away from the faucet. So I'm curious, I'm a curious person. Let's say I knew the diameter of my faucet. All right, let's call it D faucet. Let's say that was known, and let's also say that I knew the velocity of the fluid coming out of that faucet. I might be interested in, hey, if I let this faucet drip down some distance down here, I might be curious, what is the velocity farther down in the flow? Maybe let's call it the velocity of the stream at some point later on. And I might be curious, how has the diameter of this stream narrowed down later, farther down in the flow. So I might be curious, if I started off with some diameter of my faucet and some velocity of fluid coming out, as this fluid goes down, we observe in our everyday lives, the fluid farther down gets faster and faster as it falls. Faster and faster as some of this potential energy is converted to kinetic energy. And the diameter as we observed in the earlier part of this video, the diameter kind of necks down a little bit. So can we predict these two things given these two things? And of course we know, for this faucet, gravity is basically pointing down like this. So let's square away this faucet problem. So what's going to be our problem solving strategy? Well, we've already organized some problem info. So we're going to organize our problem info. In this case, we have two unknowns, so we're going to need two equations. So take a moment now and think about what equations might be useful to relate some of this stuff. All right, well, you probably guessed one of the equations is going to be Bernoulli, but Bernoulli's only one equation, right? So Bernoulli's only one equation, and we have two unknowns that we're looking for. So the other equation, well, if we have some system, let's define, the faucet, just the fluid stream just after it leaves the faucet. We can sort of define this as our system. And we want to relate, for example, input velocities and input areas to output velocities and output areas. Conservation of mass is also going to be helpful. So after we organize our problem info and kind of get the start of our problem solving strategy, we're going to need to do conservation of mass. And if we do conservation of mass, we're going to need to define our control volume. We're going to need to break it up into surfaces, and then we're going to need to deal with the left-hand side. We're going to need to deal with the right-hand side, which includes integrals. I guess integrals come after v dot ends. So sorry, switch the order of these two things. Right, so we're going to need to do this to get conservation of to square away conservation of mass. Right, so this is conservation of mass. We're going to do the left-hand side and right-hand side integrals and v dot ends, all this stuff. And that's going to be conservation of mass right here. Then we're going to do Bernoulli. And if we have Bernoulli, instead of defining a control volume for Bernoulli, remember, Bernoulli was defined for a streamline to relate 2 points on a streamline. So for Bernoulli, we're going to define points and our streamline. And we're gonna, once we define those points and the streamline, then we can apply Bernoulli, and we'll think about pressures, velocities, and h's as well. Then we might need to do some algebra, and we'll do some checks at the end. So this is going to be our problem solving strategy. So let's proceed with defining our control volume and then breaking it out. So I'm going to define a control volume, and remember, sensible points, well, we essentially want to relate information down here to information up here, and we have the most information kind of right as the fluid comes out of the faucet. So let's put one of our surfaces here, and we basically know that fluid coming out of the faucet crosses this surface perpendicular to the surface. Let's define another part of our surface sort of perpendicular to the flow down here, and then let's define a third part of our surface that is essentially tangential to the fluid right here. And we chose our control volume to sort of be right at the boundary of this fluid right here, because we know that fluid is going in this direction here, whereas our n is going to be normal here. And those are going to be perpendicular to each other. So that's going to simplify any dot products that we do for conservation of mass. So we'll call surface 1 our inlet, and we'll call surface 2 our outlet down here. So now we're essentially defining surfaces with these numbers here, and we'll call 3 everything else. So we can apply conservation of mass after we break up our integral. let's keep track of some assumptions here. We're assuming this faucet is in steady state, right? I turned on the faucet and then I didn't touch the valve anymore. I didn't touch the knob on the faucet. So we're going to assume we're in steady state. And we're going to assume that density is constant. So we're dealing with some, homogeneous, incompressible fluid here. We might add to this list of assumptions as we go on. So we're going to do conservation of mass, which is dt of the integral over the volume of rho dv equals minus the integral over the surface of rho times v dot n dA. And since we're in steady state, we can go ahead and just get rid of this term steady state right here, because the time derivative of anything in steady state is going to be 0. And so that means our left-hand side is now 0, and we can break up the right-hand side into 3 parts. So over surface 1, we have our known density, rho. Take a moment now, pause and ponder. What is v dot n for surface 1? So pause and ponder. What's this for surface 1? All right, well, our n is pointing up like this out of the control volume, and our velocity of the faucet's pointing downwards. So v dot n is basically going to be minus v of the faucet. And we have dA. And then we have minus over surface 2. We still have rho in surface 2. So pause and ponder. What's v dot n for surface 2 down here? Well, n is pointing down. Velocity of the stream is pointing down. And we're basically going to assume this v stream downstream. And I guess built into kind of saying that these are single velocities, we're going to assume uniform vertical velocities. And I guess that's not strictly true, because strictly speaking, this part of the flow has like a little bit of horizontal velocity as the stream kind of scoots in, but the vertical velocities are going to be way bigger than these little horizontals, so let's just neglect those. And of course we have dA, and then we have minus our integral over surface 3. We have rho, and of course v dot n for surface 3. N is pointing this way, v is pointing this way over kind of any point on surface 3. So v dot n is going to be 0. All right, so there we have it. So can we deal with some of these integrals? Well, yes. Density can come out. These uniform velocities can come out. And what are we left with? Of course, this term goes away. What are we left with? We're left with 0 is equal to rho v faucet times the integral over surface 1 dA. This, of course, is just the area of this part of the faucet, which we can cut to the chase and say this first term becomes rho v faucet times pi over 4 d faucet squared, right? The area of this faucet, we're assuming that the faucet is basically a circular cross section with this particular diameter. So there we have it. Then we have minus rho times v stream times the integral over surface 2 dA. This essentially is the area of this circular, that circular section of the stream downstream. So what do we have? We have minus rho v stream times pi over 4 d stream squared. So we have one equation, but we have two unknowns in it, and we anticipated this, right? We anticipated that we would need two equations to deal with these two unknowns. So this is one of our equations, and this is the result from conservation of mass. Of course, if we see both terms have a rho and both terms have a pi over 4, so we can just divide those out. And what do we get? We basically get v Faucet d Faucet squared is equal to v stream d stream squared. So what does this mean? Basically, we can do some physical interpretation here. Basically, at the inlet, the velocity is moving pretty slow right as it exits the faucet, and the diameter is really big. But once the fluid falls for a little bit and accelerates due to gravity, its velocity rapidly increases. And if its velocity increases, then its diameter has got to decrease proportionately in order to have both of these, both of the sides of this equation be the same thing. So there we have it. This is our result from conservation of mass. All right, so now we need to build in a couple more assumptions. If we're going to invoke Bernoulli, we need to assume that we have negligible viscous effects. For example, no turbulence. And of course, you know, this applied pretty well when the flow from the faucet was nice and smooth and laminar. But of course, if you look closer to the bottom of the sink, it kind of got turbulent and broke up into droplets and all that stuff. So this analysis basically works until the faucet starts getting turbulent. But before we get into Bernoulli, if you remember, we needed to define points and define the streamline that we were dealing with. So let's define our streamline right here. And let's say that 2 points exist on the streamline. Now again, the points that I'm defining on the streamline, strictly speaking, aren't the same, don't have to necessarily be the same numbering as the surfaces that corresponded to those points, but let's just call this point 1 as well, and we'll call this point 2 down here. One other piece of information that we take, we're essentially looking for a function of basically as a function of the distance from the faucet. We were looking for what these are from a known given distance from the faucet. So one additional piece of information that I'm saying is kind of like a known or a given in this problem is basically let's call it capital H, which is the distance between the faucet and the point in the kind of the distance down from the faucet that I'm choosing to analyze diameter and velocity. All right, so we have this information. Let's go ahead and invoke Bernoulli to help us. So Bernoulli basically said, so the pressure at point 1 plus 1/2 rho times the magnitude of velocity at point 1 squared plus rho g h1 was equal to the pressure at point 2 plus 1/2 rho times the magnitude of our velocity at point 2 squared plus rho g h2. So we have this relationship between them. Let's start plugging in particular values here. And one last piece of information to help make sense of these pressures is anytime you have some jet that's not contained within a pipe. If you have some jet or some stream or some droplets or something, if you have some jet that's basically kind of streaming through the air and is in touch with air everywhere, then so for a jet flowing freely in air, all pressures are atmospheric. So the details of this are, I guess, a little bit beyond the scope of what we can, but you can sort of just take this, the clouds opened up and Professor Landon's face came through and said, this is a truth, believe it, and then the clouds close back up. So we can just take this as a given. I guess we could put it in an assumption if we wanted to. So let's start putting in some of our known constants and stuff in this Bernoulli equation. So atmospheric pressure is basically known. So P1 is basically known. Now we have plus, we'd have 1/2 rho is a known constant, and V at point 1 is V at point 1 is V Faucet. So the magnitude of this velocity squared is basically just V Faucet squared. Rho is a known constant, of course, as is G. And I'm just going to leave H1 as something yet to be determined for the time being. Pressure 2, well, both points 1 and point 2 are points of this jet that are sort of in free contact with the air and sort of freely flowing through the air. So point 2 is also at atmospheric pressure. And we have 1/2 rho. And the velocity at point 2 is simply this downstream V stream right here. So that's squared. And then we have plus rho G, and I'll leave H2 as something kind of yet to be dealt with. All right, so what does this mean? Well, we can just cancel atmospheric pressure from both sides, and we have something that we can deal with. So if I kind of want to do some organization and grouping and all that stuff, I can. So if I have 1/2 rho V Faucet squared minus V stream squared plus rho G H1 minus H2 is equal to 0. So I'm just sort of bringing everything over to the left-hand side and factoring out some common terms. In this case, H1 minus H2 is just this capital H here. So point 1 had some height, point 2 had some height, and the height of this minus the height of this, we could define our sort of z equals 0 at any arbitrary point we wanted. The difference in these two heights would basically be this h, this distance between the edge of the faucet and the point that I'm analyzing later on. So this is what we're calling capital H. All right, so what does that mean? So how does that help us? What does that give us? Well, now we essentially have one equation here with velocity of the stream entirely in terms of known constants. This equation here was from Bernoulli. So this basically gives us the velocity of the stream entirely in terms of known constants. Then once we have that, we can plug that in up here to basically get the diameter. So what does that mean? We did Bernoulli, we dealt with pressures and velocities and heights. So now let's do a bunch of algebra to kind of solve for the things we care about and in terms of the knowns that were given to us. All right, so let's go ahead and do that. So I'm going to take the Bernoulli equation and I'm going to solve it for V stream. If I do that, well, both of these terms have have density, so we can actually get rid of that. We can multiply both sides of the equation by 2, so we end up with 2gh. Sorry, when you solve for v stream, you end up with v stream equals the square root of 2gh plus v Faucet squared, where the sum is kind of under the square root here. All right, you know, I guess you can do the algebra yourself, but I guess you could also take my word for it. Let's just double check units, that units make sense, right? We have v stream on the left-hand side. That should have meters per second. And hopefully this equals something when we take the square root of. So g times h, g is meters per second squared, and h is meters. So we have meters squared per second squared. So when we take the square root of that, we get meters per second, so that's good. And of course, v Faucet squared is meters squared per second squared. So it's okay to add these two things because they both have the same units. And then when we take the square root of it, we end up with meters per second. So we have a sensible result here. It also makes sense that the faster my faucet is going, the faster the downstream velocity is going to be. And also, the more distance, the more h I give, you know, the more h I give, the faster this has a chance to go, right? If h goes to 0, then I basically say the velocity of my stream is what I started with right at the faucet, but if I let h get big, then I give this more distance to pick up some speed, to have some of that potential energy essentially be converted to kinetic energy for the fluid. So we've successfully found what the velocity of the stream is going to be at some downstream point. Now we can use a little bit more algebra. We can basically plug that into this equation right here. Right now that we have velocity of the stream, we can plug it into this equation here and then solve this equation for the diameter of the stream. I'll spare you the steps of doing it, but you end up with d stream is equal to d Faucet times 1 over the 4th root of 1 plus 2gh over v Faucet squared. And if you check out the units, g times h is meters squared per second squared, so dividing it by v squared is fine, unit-wise. So, so that means this whole quantity right here is unitless, so we basically get something here. And what does this mean? Basically, if we allow h to get really big, then we take our initial faucet and divide it by some larger number, so the diameter of the stream should be getting smaller as h gets bigger. Although alternatively, if you turn on the faucet to be really fast, then this effect is somewhat suppressed, because that means basically the second term becomes closer to 1. So the faster your fluid comes out of the faucet, the less pronounced the diameter shrinkage is. And the less pronounced the diameter shrinkage is, and you might notice this, for example, if you turn on the faucet full blast, you notice barely any contraction of the faucet. Whereas if you turned on the faucet just barely, then you really notice that very pronounced narrowing of it. And I'll leave that up to you to experiment on your own to see this effect. So hopefully this is a satisfying result. Thank you for paying attention, and good luck with your study of fluid mechanics.